So today we are going to talk about normal forms. If you remember in the first discussion or the second, we talked about conjunctions and disjunctions. So basically a conjunction means clauses getting connected together with an and, while disjunction means your clauses get connected with O operations. Okay, so when you have a single preposition, for example, P, Q, stuff like that, you call these literals. And when these literals are connected with each other through a conjunction or a disjunction, you call them a clause. For example, if you have POQ, this is a clause. Okay, so when you have something like this, POQ, negation POR, this is a conjunctive normal form, okay, because you have your clauses which are connected through disjunctions, but the clauses itself are connected with a conjunction and operation. These type of clauses are called conjunctive normal forms. And then disjunctive means like this. So you have disjunctions or operations connecting the clauses in your formula. Okay, and then the negation normal form means that in your formula, the negation sign is only applied to a literal. For example, if you have something like this is not in the negation normal form. So you have to take this negation inside the brackets and say like this. Okay, now this is a clause which is in the negational normal form. Okay, so basically normal forms are functionally complete structures that you can present a formula in or a set of clauses in. Okay, so whenever you have negations lying outside, you take them inside the pair of brackets and keep them connected to a particular literal rather than keeping them connected to an entire clause. Okay, so when it comes to the truth table, of course, you know.
You are breaking.
Oh, I'm breaking.
Yeah.
Let me change the network and see.
We couldn't hear you from the beginning.
How is it now?
Now it's okay.
Okay. So did you hear these stuff?
No,
Oh,
just breaking.
okay. So we started talking about normal form. So basically, a normal form means a functionally complete or a functionally complete structure in which you can present a set of clauses in formal verification. So first, when you have a single preposition, you call that a literal. So P, Q, whatever the letter in the alphabet, those are literals. And when these literals get connected with disjunctions or conjunctions, those are called a clause. Those are called clauses. Okay. So when it comes to the conjunctive normal form, which is one of the structures in which you can present your formula, what happens then is within a clause you have disjunctions, but the clauses itself are connected with conjunctions. Okay, so that is conjunctive normal form. When your clauses are connected with AND operations, that's a CNF. Then when it comes to a disjunctive normal form, inside the clause you have conjunctions, but the clauses are connected with O operations or disjunctions. Therefore, you call that a DNF or a disjunctive normal form. Okay, so you can present your formula in a CNF format or a DNF format, or you have this thing called the negation normal form, which basically means that the negations in your formula should be applied to a single literal in that formula. For example, when you have a negation operation which is applied to this entire clause, you're not going to keep it like that. You're going to take it inside the pair of brackets and simplify it to this format. Now this is okay as a clause in NNF. Okay, so whenever you are asked to convert a given formula to a normal form, you need to do this operation as well, so that you take your negations inside to a particular literal rather than keeping it for an entire clause. So when it comes to truth tables, of course, you know how we can get the DNF and the CNF. So when we are looking for the disjunctive normal form, you select the true outputs that you have gotten in your truth table, and you take the literals who are involved in generating that output. Okay, and you connect your clauses with, you connect your literals inside a clause with and operations, and your clauses will be connected with O operations. So basically when you take the first one, it's P1, P2, P3. So P1 and P2 and P3. And you take the second one. When you meet a false operation, you put the negation for that literal. Okay, same goes for the third one as well. So that is how we generate a disjunctive normal form through the truth table using the true outcomes. And the opposite happens in a CNF. What happens here is you choose your false outcomes, the ones that gave you false, and you choose those combinations. So when it comes to the first one, P, Q, R, all of them are false in this case, and the output is also false. So how do you write the CNF in that case? You have your P, literal, Q, and R all to be false. Now, since the operation output is also false, you're not going to put the negation here. You take the positive form of the literals when you write the CNF in this case. Okay, so you have clauses getting connected with AND operations, but inside the clause you have your O operation. So take the positive form P, Q, R, P, O, Q, O, R. In the second one, you have these two are true, therefore you have negation P, negation Q, and R. And in the final one, all are true, therefore you have negation Q, negation R. So inside these you have the O's, and they get connected with an AND operation. Okay, so that is how we generate a CNF format using the truth table. Now, the type of questions that you might encounter is, given a particular formula, how are we going to convert this to normal form? It could be a DNF, it could be a CNF. We might have to decide which one we are going to go with the pattern of the with the pattern of the given formula. So what are the steps that we have to follow in order to get a normal form out of a given formula? So the first step that you would take is you're going to eliminate your by implications and implications, because it's not going to be helpful in converting these to an NF. Whenever you encounter by implications or implications, you're going to replace them with the normal thing that we know. P implies Q is similar to this, okay? And then the other one, P double implies Q. If we talk about this, now you know that this means P by implies Q means P implies Q and Q implies P. Yeah. So if you change the pattern of this first bracket, it's going to be negation P O Q and negation Q O P. Yeah. So now you see that this is in the format of a disjunctive normal form. Sorry, conjunctive normal form. It's a CNF. Yeah. So whenever you come across a by implication, and if you want to keep your answer as a CNF, you're going to use this answer. You can directly use it. And if you want to represent it as a DNF, what do? You take your laws that we have studied before, and you can say negation P and negation Q, or Q, P and Q, or Q and P, or whatever. So if you want to keep your answer in a DNF format, you can choose this when it comes to normal forms. Okay, so depending on the rest of the formula, rest of the clauses in the formula, you can say, you can choose which one you're going to go with. Okay, so you will get rid of your implications and by implications using either this or these. That's the first step you're going to do. And after that, you will push your negations like we discussed before. You will push your negations inside the bracket so that literals, the prepositions, get the negations, not the clause. Okay, and then you will arrange your clauses in a way such that inside the clauses you have a particular type of operation, and the clauses itself get connected with the other type of the operation, either disjunctions or conjunctions. Okay, so let's look at an example. So you have negation P or negation Q implies P by implies Q. Okay. Okay, so when you have something like this, let's get rid of the implication. So to get rid of the implication, I can say this is negation of the first part or the second. Yeah. So this gives me P and Q, or this. So as you can see here, if I forget about the by implication part for now, and if I focus on this, you see I have and inside the bracket, and here I have an O operation, which means this is going towards a DNF, right? I'm getting pushed towards a DNF format. Therefore, I shall use, to get rid of the by implication, I shall use this, the DNF representation of the by implication. So I'll go with P and Q O You can do these steps here if you want. I'll take it right away. So I can say negation P and negation Q, O, P and Q. Sorry. I have a negation sign there. So I can say negation P and Q, O, P and Q. Yeah, so use this. Why? Because I saw that over here I am getting directed towards a DNF format. So now I can say, okay, this is the normal form and this is in DNF. So we were not told initially which type of normal form to convert this to. Therefore, we say this is the normal form and this is in the DNF format, right? Let's look at another one. By the way, this example is there in the VLE activity. So coming to part D in the first question, earlier we did part A. So here you have P implies Q. Implies R. Part E is also in the same line, it has to be entered to the next line. Okay, so now if I get rid of the implication in the first pair of brackets, I have negation POQ implies R. Now if I get rid of the next implication, I have negation of the first one, OR, which means I have P and OR. Now I'll choose the literals in a way. Now this doesn't actually come under a type of a normal form, so I have to somehow join my literals in a way that that they're presented as a normal form. So I'll connect each literal with R. I have POR and QOR. Now these are in a conjunctive normal form. Okay, so it is, we say it's a functionally complete representation. Functionally complete as in your representation, your formula is represented using literals, conjunctions and disjunctions, and negations, where the negations are applied to a single literal, not to an entire clause. Okay, that is the representation that you use when it comes to normal forms. Okay, so now we talked about CNF and DNF. There's another normal form which we will be talking about a bit later, which is called a Prenex normal form, which can be applied to predicate logic as well. Let's go to that in a bit. Now we are coming to resolution principle, which I think you remember we discussed this during the previous lectures as well. And we gave it a symbol also, where we said negation E. So what did we say basically happens here? For example, let's say we have a clause saying COM, and we have a negation M. What did we say? When you simplify these two, you can cancel out this positive and the negative form of the same literal, and your conclusion is C. And we said this is negation E, which is given by the resolution principle. It's an inference rule. Okay, so now we are going to give it a formal definition. So the definition of resolution principle is that when you have two clauses C1 and C2, so a clause, and now you know what a clause is, that thing. So you have two clauses C1 and C2. Okay, and you have a literal You have a literal in this scenario, just like here, M is a literal. And what happens to M is that in the first case, M is in the positive form, and in the next case, M is in the opposite or the negative form. Yeah, so here, L1 is here in the positive and here it is in the negative form. Therefore, what can you do? When you simplify them, you're going to delete that literal from your clauses, and you say that the resulting clause is the disjunction between C1 and C2. You discard the literal which is in opposite forms in the two premises. Okay, so that is what is called the resolution principle, and it's an inference rule. Okay, so we use this in the previous sums as well. The things we discussed last week and the previous week, we used the resolution principle to derive answers. Today, let's do a simple example to see how the resolution principle works. Okay, so if we look at the third question in the activity, in the VLE, the third question says, prove the following argument, prove that the following argument is valid using the resolution principle. Okay, so you're being given literals here, the propositions are given to you here. So it says, if today is Friday, which is given by F, if today is Friday, then I have a test in CS, then I have a test in CS, or a test in mathematics. That's the first one. And then if my mathematics lecturer is sick, okay, if that guy is sick, then I will not have a test in mathematics. I will not have a test, which means negation M. Yeah. Then today is Friday and my lecturer is sick. Today is Friday and the lecturer is sick. Therefore, I have a test in CS. Therefore, the conclusion is I have the test in CS. Okay. So these are the premises and this is the conclusion I have. Now, here itself, I'll convert these two into the form that we are comfortable with. So I have negation F, O, negation S, O negation M, right? Okay, so now let's take the premises down. This is a premise. Negation S, so premise, and number 3 is F and S, that is also a premise. Okay. Now I want C. So what should I do? Now since I have a conjunction in F, sorry, in 3, in premise number 3, I have a conjunction. Therefore, I will take F out of it, okay, which is simplification. So it was a conjunction. I eliminated one person. Whom did I keep? I kept the first one, the first literal, and I used the third premise. Okay, so now I have F to be true. Similarly, I'll choose S as well. Again, I am doing the same thing. Okay, now since I have F and S, if you look at F and this one, you see that F is positive here, it's negated here. Therefore, I can choose COM over there. How do I choose COM? I'm using resolution principle there. So I'm using the negation E, which is the resolution principle, on 1 and 4. Okay. Similarly, I have S here. and negation is here. So I get the result negation m. Again, this is the resolution. Okay, then look at these two. You have m and negation m. Again, you can use the resolution principle and say C is the answer there when you put resolution to these two. Negation E, 6 and 7. Yeah, so you see that the conclusion that you got is the conclusion that you are asked to get. So you're going to have the mathematics, sorry, CS test, right? So this is the usage of resolution principle when it comes to using inference rules to prove a particular conclusion that's given to you. Okay, so we discussed some of the examples in the previous weeks as well. And now we're going to talk about something called Horn formulas, which is something that we already know. So it's a name given to a clause which contains at most one positive literal. Okay, a clause which contains at most one positive literal, at most. So that's the maximum number of positive literals you can have. Okay, so basically when you take this example over here, your x is a positive literal and the others are negative. Okay, so when you have such clauses in your formula, you call that a Horn formula. Okay, and remember that when you have a formula like this, where you have a positive literal and the others are negative, you can represent this as an implication like this. Because since you know that negation POQ is similar to P implies Q, here you can say that Y and V implies W. Yeah, so this could be one. Hello. I didn't know that I have gotten disconnected. Can you tell me where I got disconnected?
Like few seconds ago.
Oh, okay. Okay, so we were talking about Horn formulas. So when you have at most one positive literal in your clause, you call that a Horn formula. And when you have a clause like that, you can represent it is in an implication, saying that, okay, Y and V implies W. Okay, so you can't see the screen. Why can't you see the screen? How about it now?
No, saying has started sharing screen, but it's not showing.
Do you see it now? Do you see it now?
Not yet.